Good morning, everybody. Today we shall discuss about the AC analysis of a differential amplifier. First, we shall analyze the differential amplifier for the uh, differential mode gain, and subsequently we shall discuss about the uh, common mode gain. Please note that a differential signal is a signal uh, with when Vi1 is equal to Vi2 is equal to Vs by 2, when Vi1 is equal to minus Vi2 is equal to Vs by 2, the differential signal is equal to Vi. So Vi1 minus Vi2 is the differential signal, and that is equal to Vs. So please note that by selecting an input like this, we are ensuring that the common mode signal is 0. Common mode signal is Vi1 plus Vi2 by 2, and that is 0, whereas the differential signal is Vs. Hence, so we apply plus Vs by 2 here and minus Vs by 2 here, and analyze the performance of the circuit. So with this kind of differential signal, so what is the kind of output voltage you get here, and then the expression for the gain can be obtained. Please note that these two transistors are biased at 0 potential for the base. Hence, when in the absence of the signal, so the input is just grounded. Now, when you apply a small Vs by 2 at the input of the first transistor and with opposite sign at the next transistor, so there we expect an increment in the base current, the biasing base current, and the alternating current, base current would be IB, and that is responsible for an alternating emitter current IE. And since the voltage here, so this is minus Vs by 2 is here, and since the voltage here is equivalent to this and it is an opposite phase, the alternating current, so that appears here, is minus IB, so that is equivalent to this base current itself, and so this current, alternating current, is minus IE, assuming that both the transistors are identical. Since an IE flows here and minus IE flows here because the signals are opposite in phase, what is the net alternating current flowing through the resistance? So the net alternating current flowing through this resistance is 0. Hence, the biasing current, so that is flowing through RE, is what appears even after connecting the sources here. That means there is no change in the potential at this point because there is no alternating component here. So in which case, so this one appears at a fixed voltage. For instance, in this particular application, if these two transistors are silicon, so the voltage drop, DC voltage drop, is of the order of 0.7 volts, and the base potential, DC base potential, is 0. Hence, So this would remain constant at minus 0.7 volts. The emitter terminals remain constant at minus 0.7 volts, fixed. So even if there is a change in the signal here, that means even when an alternating signal is connected here and here, so this potential remains constant. That means as far as alternating signals are concerned, it is like a short circuit for the alternating signals to the ground, because irrespective of the signal, there is no change in the potential here. Irrespective of the current, there is no change in the potential here. That means this is like a short circuit to the ground. Hence, the equivalent circuit for, in this case, is so like this. So the equivalent circuit is like this. And this is the output voltage V naught. And here you have Vi by 2, I'm sorry, Vi 1 is equal to Vs by 2, and here it is minus Vs by 2. Now let us analyze the circuit and see how much is the differential gain. Now if you draw the equivalent circuit of this particular circuit, so we find that these two are now isolated. These two stages are now isolated because this is connected to the ground, and whatever is the signal applied here, the same signal is applied here with opposite sign. That way these two are connected, but please note that this side current doesn't affect this side current. Hence, if we analyze this part of the circuit, that is good enough to give us the gain. Now with Vs by 2 applied here, this is like a common emitter amplifier circuit, and with input equal to Vs by 2. Now therefore the voltage gain we get in this circuit is like this. So the voltage gain we get for the right hand circuit is equal to naturally beta RC by RE by RI, that input resistance, and that is equal to, so beta this is equal to RC by R small e. So this is the resistance, I'm sorry, so small RE is the voltage gain. Since the input signal is minus Vs by 2, or between the input signal and the output signal the voltage gain is with a negative sign, it is equal to minus RC by RD. Now the differential gain, please recall that in the circuit here we have RE, and rather beta RE as the input resistance, and the current source is equal to beta times IB, and that current flows through RC. Hence we get the voltage gain expression, we get an expression for the voltage gain as minus RC by RE, or in terms of the H parameters, so this is equal to minus HFE RC divided by HIE is the expression for the voltage gain, a single stage for a single stage transistor. Now let us obtain an expression for the differential gain from this expression. Now the differential signal Vd is, so Vs by 2 minus of minus Vs by 2, therefore this is equal to Vs, that is the differential signal, because the differential signal is the difference between Vi1 and Vi2. Hence, this is Vs by 2 minus of minus Vs by 2. Therefore, the differential signal is Vs itself. And what about the output voltage? And the output voltage now is minus RC. This voltage A is equal to the output voltage V naught by Vi2. This is the voltage gain. And now Vi2 is equal to Vs by 2. Input voltage is, hence V naught is equal to minus RC minus of minus, it is equal to plus RC by Re into Vs by 2. Therefore, the differential gain is equal to RC by 2 Re, and this is equal to HFE RC by 2 HIE in terms of the H parameters. So please note that here I like you to emphasize one point. For a differential signal, to have only a differential signal and no common mode signal, you should apply some signal here and with an opposite signal with an opposite phase here. And with the opposite phase signal, the gain is negative. With the in phase signal, the gain naturally would be positive. So with this minus this, the signal is double the signal applied here, and because the signal applied is twice and the output is equivalent to that of that for the same signal on one side, which is half, we get the differential gain as a positive common emitter voltage gain with a factor 2 in the denominator, with 2 in the denominator. Hence, the differential gain is HFE RC by 2 HIE or RC by 2 RE. And typically, the gain is of the is a few hundreds for a single stage difference amplifier, because in a common emitter amplifier, that is what we get typically. Any questions on the differential gain?
In the circuit, the VB should be constant as a 0.7 ohms, but it is minus 0.7 and we apply VA there, sir. The difference.
Yeah. Please note that here, this is in the absence of the signal, the input is grounded, and this is 0.7 volts. Therefore, with respect to base, emitter has to be about minus 0.7 volts. So that is the biasing voltage. With some delta added here, it would be 0.7 plus delta here, and it would be 0.7 minus delta here, because it's minus delta here, so 0.7 minus delta. Hence, this terminal voltage remains at minus 0.7 itself, and this is because of this delta. So the base to emitter potential is 0.7 plus delta, and this is 0.7 minus delta. So it is valid. So this voltage remains constant, but still there is a differential base to emitter potential. When we include the alternating signal in the DC voltage to exhibit the instantaneous voltage there. Now let us obtain an expression for the common mode gain, because we are interested in finding the common mode rejection ratio of a single stage differential amplifier, because the CMRR is also an important parameter, of a differential amplifier, and we want this parameter to be as large as possible. And let us see in this particular practical circuit which is given to you, how much of CMRR you can get. So in the process, we need to determine the common mode gain of the amplifier. Common mode gain. To have a common mode signal alone and not to have any differential signal, now we have to apply a signal which is in phase at both the places. We apply plus Vs by 2 here and we apply plus Vs by 2 here. So in which case the common mode signal is equal to, I'm sorry, there is a difference. We apply Vs here and Vs here, so that the common mode signal is equal to Vs itself, the average of these two. Whereas the differential signal is Vs minus Vs is equal to 0. So when we apply a common mode signal here, what happens to the situation? So there is an incremental base 2 emitter potential here and there is another incremental base 2 emitter potential here, because of which some alternating IE flows and a similar alternating IE flows without any phase shift. Therefore, the current that flows through this resistance Re now is equal to 2 times IE. Hence, this does not remain constant and this voltage does not remain constant. Hence, we have to take Re into account, and by taking Re into account, we can draw the equivalent circuit in this fashion as given here. So let us use the approximate Re model. For the first transistor, so this is the base current IB1 and this is the model for the first transistor, and to this we have connected RC, and through the supply it is the other end is connected to supply, and supply is like a short circuit for alternating signals. Therefore, this is the equivalent circuit for the first transistor, and here is the equivalent circuit for the next transistor, and the current is IB2. So this current source is similar to this, it is equal to beta 2 IB2 if these two are beta 1 and beta 2 are the respective AC gains, short circuit alternating gains, gains for the alternating signals in for transistor 1 and transistor 2 respectively. When these are identical, beta 1 is equal to beta 2, and this is connected to RC, and this is grounded, this is not grounded. So this is emitter 1, this is emitter 2. Now both are connected together, and these are connected through Re to the ground. It's these are connected to minus VEE, which is like a short circuit as far as the alternating signals are concerned. Therefore, it is a ground. So this is the output point VO2, and this is the output point VO1, and here we apply Vs by Vs, and here also we apply Vs. And please note that with this one being IB1 and this one being beta 1 IB1, so what flows through this is 1 plus beta 1 into IB1, and similarly here that is 1 plus beta 2 into IB2. Now when beta 1 is equal to beta 2. That means when the transistors are identical, beta 1 is equal to beta 2 and IB1 is equal to IB2 when the signal is the same. Hence, the current flowing through RE is equal to 2 into 1 plus beta into IB. I am assuming that both the transistors are identical, in which case IB1 is equal to IB2 is equal to IB and beta 1 is equal to beta 2 is equal to beta. Now, we can isolate one stage from the other, or you can keep it as it is one and the same, but if you write down the equations on one side, the analysis would be clear. The input signal is Vs, because of which the current that flows is IB, and because of this IB, beta to beta IB flows here, and it is as if this resistance is as if its value is equal to twice Re. If you assume that the same current beta plus 1 into IB is flowing through this, actual current is 2 into 1 plus beta into IB, and so this is as if this resistance is equal to the voltage drop here is equal to 2 into 1 plus beta into IB into Re. And if you want the same voltage drop to be shown with this current itself, it is possible when this Re is equal to 2 Re and this stage is remote. Therefore, the analysis can be carried out with one stage itself with Re replaced by twice Re. I repeat, for the same current that flows 1 plus beta IB from here and having Re here is same as not having this and only having 2 Re resistance here, because the voltage drop here is equivalent to 2 into 1 plus beta into IB into Re when both are there. The same thing can be obtained with this current equal to 1 plus beta IB itself, but the resistance equal to 2 Re. Hence, if you analyze this side, it is clear and it is good enough, and one can determine an expression for an output voltage in terms of the input voltage Vs. And please note that the common mode signal also is equal to Vs, and that gain gives us straight away this stage's gain gives us the common mode gain, and we can obtain the common mode gain expression as beta RC divided by beta Re plus 2 into beta plus 1 into Re, which is approximately equal to Rc by 2 Re. I like you to recall the analysis of a common emitter amplifier with an emitter resistance. When you have a common emitter amplifier with emitter resistance, the voltage gain is obtained as beta Rc by beta Re plus beta plus 1 into Re, and that is approximately equal to Rc by Re itself. So that is approximately equal to the resistance ratio Rc by Re itself, and because of which its gain is low, and we were using a bypass capacitance to bypass the emitter resistance. So please recall that analysis, and if you recall that analysis, so you will find that you will get the same expression. You are getting the same expression here except for this 2, and this 2 is coming because of the reason I have mentioned, that since an equivalent current is coming here, it is equivalent to having a resistance of 2 Re. hence this is like this. And if RC and RE are of the same order, the common mode voltage gain is approximately equal to half 0.5, and there is a sign here. The sign here is equal to with an there is the sign is a negative. There is a negative sign here. It's equal to minus RC by 2 RE, because this side, this is the input signal Vs by 2. With increased input signal, there would be increased voltage here. With increased voltage, there will be an increased current here, and the current would be in this direction, and this current would flow through RC in the opposite direction, and for this reason VO2 will be of a negative sign. Hence there is a negative sign here, and it's equal to minus beta RC by beta RE plus 2 into beta plus 1 into RE. So this is the expression for the common mode gain, and as I mentioned, it is very small. Now let us obtain an expression for the common mode rejection ratio. We got the differential gain as RC by 2 RE, and we got the common mode gain as minus RC by 2 RE. Therefore, CMRR is the modulus of AD by AC, which is equal to RC by 2 RE divided by RC by 2 capital RE, and this is equal to capital RE by small re. And please note that small re is of the order of a few tens of ohms, whereas re is typically very large, hence the common mode rejection ratio is very large. Now, if we want to increase the common mode rejection ratio of a differential amplifier, we have to increase this emitter resistance Re. Now, how do you increase the emitter resistance Re? Well, by biasing with proper voltages and proper resistances, we can see that Re is large. But there is another way by which Re can be increased. If you replace Re by a common a current source, a constant current source, and its value is fixed at IE, then please note that the resistance Re, equivalent resistance Re, can be infinity. Now, with a constant current source here, with Re replaced by a constant current source equal to IE, IE by 2 flows in here and another IE by 2 flows in here in the absence of the signals, and the biasing is done such that if you want 1 milliampere here and 1 milliampere here, you make it a 2 milliampere current source. Now, under differential signals, there would be an incremental alternating current here, and there will be a current with opposite sign here, and there is no change in the current flowing through this. The alternating signal is 0 actually. So, the instantaneous current does not change. Hence, there is no problem. By using a constant current source here, it does not affect the differential signal. You can see that it does not affect the differential signal. Now, for common mode signals, when we apply a voltage which is equal and in phase to both the inputs, we expect some increase in the emitter current here and an increase in the emitter current here, and we expect a tendency to increase this emitter current. But if you use a constant current source, so the constant current source does not allow the current to increase. What happens when this voltage is increased by Vs times? The constant current source output voltage also will increase by Vs, and it keeps the VBE constant and same IE, no additional IE, alternating IE, and hence this current will remain constant. What does a constant current source do? A constant current source draws or drives equal amount of current irrespective of the voltage drop across this. So when you apply a signal here, this constant current source, what the constant current source does is, it will elevate its emitter potential equally to this input signal. That means VBE still remains 0.7 volts irrespective of the alternating signal here. If you apply an alternating signal like this VBE will be minus 0.7 plus this alternating signal. So with that, that means the voltage here is changing, but the current still remains high. Hence, the only biasing current flows and no alternating current flows through RC. Hence, for the common mode signal, the gain is 0 ideally, and that is equivalent to having an RE which is infinity, because when you use a constant current source, the impedance of a constant current source is infinity. So common mode gain is 0 and CMRR is infinity. So this is about differential amplifier, and please note that to increase the common mode rejection ratio in a practical circuit, we use many such stages of differential amplifiers. Here is a differential amplifier. You get the differential outputs here. You use both the differential outputs as the input to another differential stage, and then you will get the differential outputs here. So if the common mode rejection ratio is rho 1 here and rho 2 here, the overall CMRR, common mode rejection ratio, is going to be rho 1 rho 2. If it is 1000 and this is also 1000, it is going to be 10 to the power of 6. And for differential gain, if AC1 is the differential, AD1 is the differential gain here, and AD2 is the differential gain here, you are going to have a differential gain of AD1 into AD2. Similarly, common mode gain of AC1 into AC2. Hence, CMRR of rho 1 into rho 2. So in practice, we use a cascade of several such circuits to get a differential amplifier with high common mode rejection ratio. Any questions? When RE is 0, capital RE is 0, yes. No, we are not making the RE equal to 0. We are not making RE equal to 0. The situation like RE equal to 0, please note that here is a question that when RE is equal to 0, CMRR should be 0. How is it that we are getting high CMRR? Please note that the situation of RE is becoming 0 is arising only when you apply a signal here Vs and minus Vs here. Only in that case there is no change in potential and this is equivalent to ground. But in this situation where you have common mode signal, that means Vs here and Vs here, it is not like that. RE is equivalent to an infinite resistance if it is an ideal current source. If it is a practical current source, the resistance is equivalent to several hundreds of kilo ohms. Hence, you get a high CMRR. Not infinity, but a high CMRR. Any other question? Questions? If there are no questions, let me give you a brief introduction to operational amplifiers. An operational amplifier is basically a difference amplifier with single input, and the symbol for an operational amplifier is as given here. So this is a non-inverting input and this is an inverting input, and you have one output terminal here, and it is a differential amplifier to start with because it has two inputs and it amplifies the signal, the differential signal between both the input points. That means if you apply here a signal equal to Vi1 and apply here a signal equal to Vi2, what it gives at the output is equal to AD times a strong gain. Let me call it A itself, A times Vi1 minus Vi2. So it amplifies a different the different signal. The common mode rejection ratio is very high and the common mode gain is almost 0. So its characteristics are as follows: very high voltage gain, which is of the order of tens of thousands. So very high input impedance, it is of the order of mega ohms, and if you use FET input op amps, it is of the order of giga ohms or hundreds or thousands of mega ohms. So very low output impedance, and output impedance typically is of the order of 50 ohms, and large gain bandwidth product. It is of the order of 1 megahertz in the case of operational amplifiers like 741, and today there are operational amplifiers available with bandwidth which is of the order of 1 gigahertz. Ideally, we want the voltage gain to be infinity, input impedance to be infinity, and output impedance to be 0, and gain bandwidth product to be infinity ideally. But practical circuits do provide something much lower than this. So an operational amplifier is basically a differential amplifier with single output terminal. And now let us see how an operational amplifier can be used. By grounding one of the terminals and using only one terminal, say the negative terminal, and grounding the positive terminal, we can use it as a single-ended amplifier. Just as an amplifier with voltage gain is equal to, with voltage gain is negative with a negative sign. And with this circuit itself, by applying an input between these two and taking the output here, you can make use of it like a double-ended amplifier. By connecting a difference signal across these two terminals, it can be used as a double-ended amplifier. Now, for analytical purposes, the equivalent circuit is as follows. Like any amplifier, between the two differential inputs, so it has a differential input resistance Ri, and it amplifies the signal with a high gain, high voltage gain. If this is the difference signal Vd, this is AVD is the output voltage, and the output voltage is not independent of load because it has some small output impedance or not. So the output side equivalent circuit is like this. So this is the equivalent circuit of an operational amplifier. And please note that the input can be isolated from the output terminals. If you ground one of these terminals here and ground this terminal, say this terminal as a ground, then there is a common reference between the output and input, and it acts like a single-ended amplifier. Otherwise, these two are isolated. But if you are using it in the differential configuration and apply a difference signal here, you can ground one of the output terminals and tap the output signal, so like this. So please note that none of these terminals are connected to the ground, they are isolated unless you force one of the terminals to be grounded through an external connection. So this is the equivalent circuit of an operational amplifier. Do you have any questions on the operational amplifier and its equivalent circuit? If there are no questions, I'll stop the lecture here and continue it in the next class.